Hello everyone, I'm Emma, a final year medical student at Cambridge in the UK, but I did what you'd call an MD PhD programme, and my PhD was in machine learning for healthcare. This is work that I did in collaboration with Joanna Beaker, who now works at DeepMind, Pietro Leo, my PhD supervisor, and R2HCAI-23, a consultant anaesthetist working in critical care and trauma. As I'm sure most of you already know, mechanical ventilation refers to the process of ventilating a patient's lungs using a machine. There are a number of reasons why we might want to do this, but we can broadly divide the patients into two groups. So those with relatively healthy lungs and have just had surgery or need to be deeply sedated for other reasons, versus those who have varying degrees of lung failure and need further support with their breathing. Patients on mechanical ventilation are a highly heterogeneous group with widely differing outcomes, but we don't have robust evidence-based treatment protocols for different types of patient. And because patients have such high mortality on ventilation, even a small improvement could make a big impact. So the focus of our work is to cluster the patients into useful subtypes based on their phenotype and their outcomes. This would be useful because the clusters could be used to create interpretable early warning systems to alert clinicians of deteriorating patients, or they could help us to study and understand subtypes of disease. And finally, they could be used to subtype a patient early on in their admission so that we know how to personalize their treatment right from the start. So we use a data set from Amsterdam, which contains almost 15,000 ventilation episodes. We have 31 time series variables like heart rates, blood pressures, and some static information like sex and ethnicity, which don't change during the patient's stay. So this slide shows how we perform the clustering. So the time series for each patient are given to an encoder to produce an embedding, shown in green. And this is either an LSTM, a transformer, or a temporal pointwise convolution model, which I previously published in 2021. The embedding is trained in a supervised way to predict the four outcomes shown in red. So mortality, the chance of receiving a tracheostomy, which is a tube that is inserted directly into the windpipe via the neck. And then we have two duration tasks, which are length of stay and the ventilation duration. These tasks ensure that the outcome information is contained within the embedding, and we also include some unsupervised tasks to reconstruct various aspects of the input. And finally, we have a forecasting task, which predicts the next time step ahead, helping to embed the trajectory of the patient. And once we've trained the embeddings, we can then perform k-medioids clustering to generate the embeddings. So the first thing that we did was to compare the results from training different encoder models. Here we're showing the area under the receiver operating characteristic curve on the binary task, so the mortality in blue and the tracheostomy task in red. And we can see that the best performance is gained by the TPC model. Next, we're showing the results on the duration task. So this graph is showing the mean squared logarithmic error, where for this metric, lower is better. So again, the TPC model performs the best here. And from here on, we're using the TPC model as the main model for the subsequent cluster analysis, although I'll come back to the other two encoders later on. So taking the TPC model, we used the ELBO method to identify 5 clusters that had good intercluster separation. And I'm going to take a bit of time to explain the various clusters that we have here. So on the left, we've got an acute pulmonary injury cluster, which have a mortality of 72%. And if we look at the data itself, they have very poor lung function. So we're thinking impaired gas exchange and stiff lungs. You know, it's not good to be in this cluster. Next, we have a pulmonary critical illness group where the patients stay a bit longer in the unit, and sometimes they get tracheostomies to facilitate longer term ventilation. And they have moderately poor lung function, so this is forming a more chronic picture of disease. The third cluster have very good outcomes, and they're mainly formed of surgical patients who are briefly admitted in the immediate post-operative period, but they recover quite quickly and are discharged. Cluster 4 is interesting because the patients have good outcomes and good lung function, but they're ventilated for an extended period of time, which suggests that they're recovering from damage to another organ in the body. So we call this the general critical illness subtype. And finally, the last cluster contains acutely unwell patients who are often admitted due to decompensated failure of another organ, such as the kidney, the liver, or the heart. But the lungs aren't the primary source of pathology here. If we look at the embedding space itself, we can see how the clusters relate to each other and how the outcomes are nicely distributed across the representation space. It's also reassuring that when we look at the transitions between clusters from one time point to the next, the patient is overwhelmingly most likely to stay in the same cluster. And this is despite not having any explicit temporal smoothing loss function. And in fact, when we plot how many clusters the patients appear in during their stay, the vast majority only ever appear within one cluster during their stay. And in addition, most patients are placed within the cluster that will become their main cluster, so the cluster that they end up spending the most time in during their admission. Most of those, or about 75%, are in that cluster from the first hour of their stay. So this is something that we can identify very early on. Obviously, none of this cluster analysis means anything unless we can trust the clusters that the model's giving us. So we changed many aspects of the setup to see if we would get similar clusters. So I'll go through these in turn. So here are some heat maps showing which cluster the patient's placed in using different encoders, comparing two at a time. So this allows us to see which clusters correspond to one another. So we can see a fairly high degree of agreement between some of the clusters, especially between the TPC and LSTM and the TPC and the transformer. And we found that where there are discrepancies, we found them to be because of slightly different placement of the decision boundaries between clusters in the representation space, rather than them picking out a completely different set of characteristics. We performed a similar study with different random seeds for the TPC encoder, and this showed a greater degree of reproducibility, as expected, because it's the same encoder. And finally, we looked at what would happen if we vary the number of clusters. So this is interesting because we noticed that as we progressively add clusters, the clusters seem to slot into the existing structure of the clusters rather than completely disrupting all of the decision boundaries between clusters. And this is encouraging because it means that we're picking up consistent phenotypes, and these then get subdivided. Finally, we had a look at the transitions between clusters. So these are moments where the model thought the patient was progressing in one direction, and then something happened to change the trajectory of the patient. And we noticed that the outcomes following these events tended to reflect the outcomes of the destination cluster rather than the origin cluster, which makes sense. And we're performing further analyses on these cluster transitions because we believe that they could reveal some important causal factors which could influence outcomes or identify important time points in which we could intervene to change the eventual outcomes. So to summarize, we've shown again that the TPC model outperforms alternative encoders, which is consistent with data in MIMIC and EICU. We've also shown that we can generate meaningful and interpretable clusters. The clusters are remarkably stable across time, and the model usually knows immediately what type of patient this is, which is promising for designing intervention strategies which target particular types of patient in the future. And we're doing ongoing work to characterize the transition points between clusters, which we believe could be insightful in future work. So that's the end of my talk. Thank you for listening. Thank you to my funders and also the workshop organizers.